Good afternoon and welcome back to Icmpma 2022. We now move on to the 8th session of our conference and the second session of the day on the topic electronic materials. We invite Dr. S.N. Poti to chair this session. Dear sir, we welcome you to start the conference.
Thank you very much. So, good afternoon to all. This is the last session. I understand that I was there in this 7th session also. So once again, I would like thank the organizers, especially Dr. Sunil Thomas, for giving me this opportunity to chair in this international conference on materials, properties, measurements, and applications. And I take this opportunity to congratulate the entire team for successfully conducting this international conference. I'm really privileged to introduce the speakers. There are 2 speakers in this session. The first invited talk will be presented by Dr. Qasim Abdullahi, Heriot-Watt University, UK. And the second talk by Dr. Sridhar Kaushik Bharadwaj from University of Amsterdam. So let me go to my duty of introducing the speakers. So the first speaker, Dr. Qasim Abdullahi, received his master's in engineering with a distinction in electrical and electronics engineering from Heriot-Watt University, Edinburgh, UK, in the summer of 2018. He is currently pursuing his PhD in electrical engineering. His research area includes compact wearable antenna, frequency selective surface, metamaterials, wearable antennas, and wireless power transfer. And the time allotted is 30 minutes. And I request the speakers to strictly adhere to the time schedule. Please note down the time of start. And with this, I welcome Dr. Qasim S. Abdullahi for delivering his lecture on thermally modified TRMC for characterization of VO2 conductivity. Dr. Qasim, please.
Hello, can you hear me?
Yeah.
Yeah. Okay.
Can you make it full screen? Yes.
Okay. How do I share the screen? Sorry. Sorry, one moment. Okay. Can you see my screen now?
Yes, please start.
Yeah. So thank you very much. My name is Qasim Abdullahi, and unfortunately, I'm not yet a doctor. I'm still pursuing my PhD in Heriot-Watt University. And I thank the organizers of this conference for giving us the opportunity to have this talk and to increase, basically to have more confidence to present work. This is my first ever talk at any conference. So thank you very much. So the title of my work is Thermally Modified Time Resolved Microwave Conductivity for Characterizing Vanadium Dioxide. So the background of the project is we're working with vanadium dioxide. So vanadium dioxide is a special oxide that undergoes phase transition from an insulating crystalline monocline phase to a metallic roctile phase at critical temperature of 68 degrees. So that temperature can vary based on the doping and some other factors. So the vanadium structure varies based on the deposition technique, which affects its material properties. So the motivation for this is the work I'm doing is in two phases. So the first phase is to characterize the material, vanadium, and for reconfigurable electromagnetic systems. And then the next phase will be to having successfully characterized the material to make reconfigurable systems such as antennas, frequency selective surfaces, reflectors, and so on and so forth. So so that's the two phases of it. So characterization of the characterization techniques. So the growth procedures and the film substrate thickness and the stoichiometry is what determines the vanadium's properties. So, and any change in these parameters can vastly change the electric and optical properties from one film to another. So at the moment, a lot of measurements of vanadium in the electromagnetic area is on trial and error. So materials are wafers are fabricated and are measured, and based on that, it's just continuous trial and error. So at the moment, there's no concrete way of verifying all the vanadiums based on the different deposition techniques. So the main interest in the characterization is the electrical and optical performance across the transition. So the transition is generally triggered by temperature change, and some characterization techniques include spectrometry, pump probe, 4-point probes, X-ray diffraction. So generally, the technique we're using falls under the general spectroscopy. So this deals with the rate of the chemical reactions and factors which influence the rates and the explanation of these rates and the mechanical and the mechanism of the chemical processes. So a time variable is introduced, and when a time variable is introduced, the rate of the change of this concentration of reactions or products with respect to time is known as the time resolved spectroscopy. So generally what we look for is the transmission and reflection parameters of our measured of the measured samples. So narrowing it down to the time resolved spectroscopy. So this is basically the study of the processes after a stimuli is applied. So such as light or pressure is applied to a sample. So in a photoelectric process, for example, when a pulse laser is used to study this process, we can get it in high speed. So basically this can be applied to different materials. So the main things to note when we're applying, we're trying to characterize a material is to determine the state of excitation, the reaction products and the reactants involved, the intermediary states, how stable the material is, and the relaxation dynamics. So the main technique we're using here is time resolved microwave conductivity. So typically, this involves a beam of light used to excite a sample, and as the transition occurs, changes in the microwave response is being monitored. So in photo applications, holographic grating is used on samples. So in vanadium, for example, during the transition from the metal to insulate, during the transition from the insulation to metallic state, we induce it by an incident light being absorbed, and then we look at the optical transmission properties of that. So the novel part of here is based on applying. Okay, so basically the technique involves applying, for vanadium, we're using the temperature as the external stimuli to excite the sample, and then it gives us a material perturbation response, which we can see clearly with high frequency microwaves. So the conductance of the materials is evaluated from the change in conductance upon the change in temperature. So the main thing here is we're replacing, the novel part here will be we're replacing the laser with, because the light being used here is to excite the sample thermally. So we don't need light anymore. So what we're doing here is we're replacing laser with low power Peltier plates to thermally generate the charge carriers. And we look at the microwave response of this. So the sample is thermally excited using a self-made thermoelectric assembly, which is made up of metallic plates and Peltier elements with a heat sink and fan. So just so here, looking into the microwave conductivity, we can characterize the phenomena as the change of conductivity based as an external stimuli is applied, there's an initial state conductivity, and as the rate of that stimuli increases, the conductivity of the material changes. And this in turn affects the reflected microwave power. So this leads to the equation here. So the power reflected over incident power. And then we look at this as a perturbation change. And we can characterize this with perturbation theory in microwaves. So the relative change in the reflected power is easier to calculate by looking at only the unperturbated microwave power. So what we do here is we multiply the two sections by the input power, and we generate a new equation here where we derive a constant here, which represents the sensitivity factor of this system. So the sensitivity factor here is the ratio of the power reflected due to a change in the conductivity of that material. So in general, like the sensitivity factor does is it measures how sensitive the microwave response of that sample is based on the applied stimuli, which is the temperature in this case. So this factor here depends on the geometry, position of the sample material inside the waveguide system, the waveguide measurement system. So based on the theory of perturbation, we can derive the quality factor of the material here, and with the quality factor, we can simplify the sensitivity factor to a smaller equation here. So here, this shows the relationship between our sensitivity factor and the microwave response of that system. Yeah, so having known the sensitivity factor and the microwave response, we can easily derive our microwave conductivity. And with this, we can easily estimate how we can easily determine if the vanadium sample is going to be useful for our application in our RF application. So, and yeah, this brings it to the end of the conversation. So just to conclude again, the project involves 2 phases. So the first phase is to characterize vanadium, and after characterizing vanadium, we can implement our electromagnetic systems and build our metal surfaces based on that. So thank you.
So, thank you, Dr. Qasim, for the excellent lecture. Now, this is open to questions now. So if anybody has questions, please ask questions.
Hi, can you hear me? Hi.
Hello.
Hi, Qasim. So do you already prepare this vanadium, or did you use the recently deposited samples?
Pardon?
How did you prepare your vanadium dioxide samples?
So it was prepared using pulse laser deposition.
Okay, so it's the one prepared at least. Okay.
Yeah.
So how do you consider its performance at the moment?
So it's based on we look at the conductivity. So the more conductive the sample is, the more microwave response it can have. So for example, here now, this shows a graph of different conductivities of different samples based on the different thicknesses that we have. So we see here that at the thickest sample is 100 microns here, and it has the highest conductivity between, so at the hot state, it has a conductivity of 3 orders, and close to the cold state, room temperature, it's almost 0. So that's how we know how effective this would be in our microwave application.
So what's the next step in the study what should be the next step?
So the next step will be, having known how responsive it can be in the microwave, we can now start to model antennas, or the first step is actually we're going to model frequency selective surfaces with the samples and see where we can go from there.
Thank you.
Okay, thanks.
So, Dr. Qasim, I have a question. Actually, how did you measure this microwave conductivity?
So I used the time resolved microwave technique. So basically here, using this waveguide system here, I was able to measure the microwave response, and I was able to calculate the sensitivity factor. So from this equation here, I was able to link the sensitivity factor with the conductivity. So having known the microwave response and the sensitivity factor, I can easily determine what the conductivity is.
So by microwave, what are the frequencies?
Here we're using 30 gigahertz.
30 gigahertz. Huh?
Yeah.
Okay, only one frequency.
One frequency at the moment, but it's applicable to a wide range of frequencies. But for our application is at 30 gigahertz, so we only looked at that.
Okay, thank you. So, any other questions? So with this, I think we thank Dr. Qasim Abdullahi for his lecture. Thank you, Dr. Qasim.
Thank you.
So we will now move on to the next speaker. Next speaker is Dr. Sridhar Bharadwaj from University of Amsterdam. So I'll introduce Dr. Sridhar Kaushik. He is nanotechnology and nanomaterial scientist with a demonstrated history of 6 years of experience working as a researcher. She completed her PhD in nanoscience and nanotechnology on the topic study on development of triglyceride biosensor based on nanomaterials. Then she worked as a research scholar in the Department of Nanotechnology at Amity University from April 2017 to September 2017. Later, she worked as scientist at the Nanotechnology Research Institute in 2018 and the postdoctoral research scientist at Polish Academy of Science from July 2018 to April 2019. She also worked as researcher, postdoc fellow at the University of Amsterdam from May 2019 to June 2021. Currently, she is an application scientist at Amsterdam Scientific Instrument, Netherlands. She received several awards and honors such as visiting scientist and scientist at his Scientific and Technological Research Council of Turkey, the Department of Science Fellowship and Grant Programs, etc. She is skilled in electrochemistry, biosensors, nanomaterials, graphene, thin films, material science, hybrid pixel detectors, and optics. Her major expertise include nanomaterials, especially graphene, synthesis and application in biosensors. She is engaged in design and development of various electroactive nanostructures for electrochemical biosensor and nanomedicine for healthcare. She has expertise in several characterization tools and good experience of surface plasmon resonance and biosensors. With this, I welcome Dr. Sridhar for delivering her lecture. Dr. Sridhar, the time allotted is 30 minutes.
Yeah.
So please.
Okay. Thank you very much for such a nice introduction. So I'm glad to present my work here. So yeah. So can you see my screen?
Hello? Yes, yeah.
Yeah, visible.
You can make it full screen.
Yeah. Full screen means.
Just wait. Yeah. I think, wait a second. Yeah, so now I think you can see my screen. Okay, so hello everyone. So today I'm going to give an overview about the hybrid pixel detectors, which are used for different applications in different fields for the characterization of various nanomaterials, thin films, and so on. So first of all, I would like to tell you that I'm working at Amsterdam Scientific Instruments as an application scientist and a project manager. So this is situated in the center of Amsterdam at the Science Park. And this is the location where we are living here and we are working at the same office. So the ASI is making the hybrid pixel detectors in the field of for the ions, for X-rays, neutrons, photons, and electrons. So today I will just discuss more about the electrons. So I will be more focused on the electron microscope detectors for hybrid pixel detectors. So yeah. So just an overview, like how the products looks like. So we have different products which we install on the various TEM instruments on various microscopes, and there we can do the various experiments and can analyze our samples over there. So I will I'm just giving you an overview that the electron detectors which we are making at the company. They are in different forms, and we call them cheetah, Medipix, and the Timepix. So they looks like this. So now I will just tell you the mechanism behind that, and what are hybrid pixels, and how they are working, and all these things. So now, what are hybrid pixel detectors? The hybrid pixel detectors, they are the detectors which can even detect a single electron, and they are made up of a very unique technology, which is the latest technology. And we can solve many structures of the materials with these detectors. And these detectors are noiseless. They have no noise. That's why we get sharp peaks, and it's easy to determine the structure of your molecule or whatever you want to study. So they are ultra sensitive, and they are noiseless detectors. So now I will tell you that why we use the term hybrid, why we call them as hybrid pixel detectors. Reason being, because these detectors, they are made up of a very unique technology, and these are the microscopic sensitive elements, each of which is connected with its electronic pulse processing unit. So we have the sensitive layer over here, which can be made up of any material, and which is bounded to the ASIC chip. So you can say that each pixel is having its own electronic unit, electronic processing units. That's how it makes them very fast. So this semiconductor layer bounded with the chip, with the electronic circuit, which is prepared at CERN, it makes it hybrid. That's why we call them as hybrid detectors. So it looks like this. You can see this is the surface of the semiconductor layer. So this semiconductor layer, it could be made up of silicon, gallium arsenide, cadmium telluride. It depends on the application. Like if you want to do your experiments around 50 kV, or if you want to go for 300 kVs, if you want to go for 200 kV. So we have different sensor semiconductor layer on the surface according to the requirement of the experiments. And yes, we have a very different size available for this. So the size, it varies from 256 pixels to 1024 pixels. So you can have a very large detector to have your electron diffraction pattern or your imaging, whatever you want to do with this technology. So I will just show you, I will just tell you the principle behind this, why we say that hybrid pixel detectors, they are the noiseless detectors. So when the electrons, they hit your sample, and after that they hit the surface, after reaching from the sample, crossing the sample, they hit the surface of the semiconductor layer of the sensor, then electron and hole pairs are generated, which pass through this bounded layer, and then the signal is amplified. After the amplification, this signal passed through a comparator, which is having a predetermined threshold. So the signal which are above this threshold, they are counted, and they are counted as one count, and we get the diffraction pattern. So this is how, because the signal which are below this threshold, they are not counted, and that's how they make these signals noise free. So this is the main technology and the principle behind these detectors. So based on this, these detectors, they are of different types. So this is the first one I will tell you about, the Medipix based detectors. So in the Medipix technology is a frame based technology. So you get n number of frames, and then they are gathered, and we get the entire final image. That is the Medipix technology. So in the Medipix also, we have two different modes of operations. That is the sequential mode and the counter mode. So I will not explain a lot about this. I will just give you an overview about like what are these modes are. So if you look into the modes, if you see the signal which are above this threshold, they are counted as 1, you can see 2 and the 3. And so this is how the signals are counted. The shutter is opening, shutter is closing. So it is counting, shutter is opening and closing, and that's how we get the signals. So in the Medipix, we get the maximum speed of 700 frames per second at the bit rate of 24 bit. But In the continuous mode, we just got the rid of this shutter closing and shutter opening mechanism. And that's how we get only count and read, count, read. So no shutter is opening, no shutter is closing. And it's not like the mechanical shutter. So this is the internal shutter within your ASIC chip, which is opening and closing. But in continuous, we got rid of this. So we have, the data is acquired and it goes directly without any buffering. So here we get the frames of around 2000 frames per second at 12-bit mode, and we can reach up to 4000 frames per second and only at 6 bits. So this is the beauty of the Medipix, that we get the zero dead time signal and noiseless signals. So then I will just give you an overview of the Timepics based detectors. So what is Timepics and how does it work, and why we need the Timepics detectors? And Timepics are the latest detectors in which you can even know the exact time of arrival. And from that, you can get the information of your molecule or your material. So here what happens, it's the same mechanism that when the electrons hit the surface, electron hole pairs are generated, and which is then goes through this comparator, and the signal which are above this threshold, so they are calculated. So the signal, when the electron hit the clock, it is counted as 1, and it counts up to the shutter is closed, and then again the second hits, the shutter opens and closes. So this is how we get the exact information of time of arrival of the electron. And the time resolution here, it is 1.56 nanoseconds. So this is the event-based detectors and how they work. So if you see at T0, there are some few events which are recorded. Okay, and if we sum these events, we get this type of image. After the time, which is for 2 nanoseconds, we get new events are recorded on our detector. And if we sum both the events, we get the image like this. And after 4 seconds, you can see there are few new events which are counted. And when you summarize, you get the image like this. And at the time of 6 nanosecond, again, we have new events, and you can see the events which are here, they are not here. So that means you can exactly know at which time, at what position your electron is arriving, and you can measure it. And finally, you get this image. So this is how the event-based detectors work, and they make the images. So this I will skip, or I can just tell you, which I already detailed, that in the Medipix, we have it is a frame-based technology, and Timepics is a time-based technology. So here we have the bit depth from 1 to 24 bits, and with the maximum frame is 700. And in the continuous mode, you get the frame rate of 2000 frames per second. And in the Timepics, we have only time of arrival, and the maximum time resolution is 1.56 nanoseconds. So this is what the ASI makes the detectors for the detection of the electron, which are based on Medipix and the Timepics. So I can just show you a live example. If you see here, this is the ASIC chip, this is the sensor. In the event-based, you get the time of arrival and X and Y coordinate, and you get the image. And in the Medipix, as it is a frame-based, so a lot of data is calculated, collected, summarized, and we get the final image. So the only difference is in the Timepics, we get only the events, and in the Medipix, we summarize and we calculate and we see the entire frames, and then we couple them, and then when we make the image. So these detectors, which are the hybrid pixel detectors, they are used for a lot of applications. So I will not explain all today. So we use these hybrid pixel detectors for 3D tomography, for 3D ED applications, like for solving the structures of various zeolites, MOFs. They are used in the pharma industries. So we can see the functionalization materials, we can study the materials with these detectors, and we can solve the structure of the proteins, and so many applications. And the latest one nowadays people are using, the hybrid pixel detectors, is for 4D STEM applications. So I will just show you how it works. So if you see in this image, this is the 4D stem in which you have the 2D scan at each scan point, plus you get the 2D diffraction pattern and you get the image. So this is the 4D stem technology for which the hybrid pixel detectors can be used. So yeah, this is how it works. So the electron probe, the electrons, they pass through the sample and we get the pattern on our pixelated detectors. And this is how we get the electron diffraction patterns to solve the structure of your molecule. So these could be used to know the heterogeneity, to know the structure defects. And yeah, it depends on the thickness of the layer also, and grain orientation. And yeah, with the pithography, which is a new technique for in the 4D stem, you can even see the structure with the thick samples as well. It depends how much resolution you want to work for. So I will just show, now I will just give you an example that these are few published papers on this technology. So this group, they solved the structure. This is, you can see the 3D precision of the electron diffraction tomography, and they solved the structure of the drug which is used in the pharma with these detectors. And here you see this group, they worked to see the 3D pattern diffraction of the hen egg with the white lysosome. So you can see the structure of this lysosome, this solved with these detectors, which I'm showing to you. And this was the another publication in which they solved the structure of a drug, again for the pharma applications. And this is the first time I think they solved this structure, because it is a very old structure which was still unsolved. And they solved this structure with the help of hybrid pixel detectors. And then again, you can see this is this group, they solved the structure and analyzed the nanocrystalline material with the help of the hybrid pixel detectors. And they can see the different diffraction patterns and then calculate and solve the structure of the material. So yeah, this is just I will tell you, like the cheetah detectors which are used for 4D stem. This we did this experiment in our lab to solve the structure and to see the copper sample orientation. So these are the images from the orientation mapping of the copper sample with the 4D stem application. And so if I summarize my entire system, we provide the detectors, which are hybrid pixel detectors. And this chip, of course, the area of the chip varies for the applications. With the high performance PC, we have our own, the software with our own scan generator and with our own trigger box. With the trigger box, you can synchronize your detector with anything which is already there. You can synchronize with any software, with any, you can do a lot of integration with the help of the trigger box. So this is an overview, like we have installed the detectors on different TAM for various applications. And yes, so we are working with different universities for the same hybrid pixel detectors, and they are really working good. And yes, I'm happy that this is the new technology for which I'm working. And yeah, so if you have any questions, you can ask me.
Thank you, Dr. Sheetal Haradwaj,
Yeah,
for an excellent talk on 4D. Maybe this is new to all of us.
Exactly.
And, yeah.
That's
And
why,
anyway,
I asked Professor Josh to just give me a platform where I can introduce these hybrid pixel detectors, because I've been from India and we have never used hybrid pixel detectors.
Exactly. But anyway, it is very nice. And now I think this is open to question, a few questions.
Yeah.
Yeah, it's me here.
Yeah, hi.
Yeah, many thanks for joining.
Yes, and
it's
first
been
of
hard
all,
for
thank you very much. Yeah, for giving me this opportunity. Yeah, and I'm sorry for the delay responses.
No problem. It's okay. I mean, I know it's been difficult for you. So, so it's just regarding this detector. So, how does it work? So we have, if you have an existing transmission electron microscope, so is that you can replace the detector with with this detector, or are you working with the manufacturers directly of the
No.
microscopes?
Yeah, exactly. So you already have a TAM with you, right? So you have the CCD detector over there, which produce a lot of noise. So what we do, we just remove that CCD and we can directly install our detector. So we already have the interface and everything, because we already work with different microscopes for Zeol and FEI and Thermo Fisher and all. So it's already a compact solution, and it's this much of space is needed, and we can just install it and you can start your experiments over there.
So within your company, so these detectors, are they, so are the chips so these are probably made in different places, isn't it? Or you get the chips made in one place, and then you assemble the whole system, or how does it?
Yeah, exactly. So if you see that this technology was first developed by the CERN.
Yeah.
So CERN in the Prague, yeah. So
yes,
we
I've been there. I saw this detector there, so that's what I was coming
exactly.
to.
Yeah. So we purchase the chips from the CERN, and after that everything is assembled at ASI, and we make these water cooling systems and everything at ASI itself. Yeah,
that's brilliant. So do you still collaborate with the CERN on this?
Yeah. Because now we have Timepics 4, and I think we got the license to sell that.
Yeah. I visited CERN and I saw these detectors there in the group of Petra Redler there.
Yeah, exactly. When I joined this ASI after completing my postdoc from University of Amsterdam, it was really new for me, because we always only just see, the time to see, okay, just the layer is there, some diffraction pattern is there. But when I entered into the ASI and saw it's a lot of things to explore, and we never used and never heard of these hybrid pixel detectors, but people are using it a lot.
Yeah, so it's a nice story, so this has been developed for the Large Hadron Collider in CERN.
Yeah.
And then they spin out it for medical and other applications. So
a lot of applications. Yes. Yeah, I just saw a few of them today, but there are a lot of applications. I just focused on your electron. You can go into photonics, X-rays, and so many things also you can do. Yeah.
Great. Yeah, thank you, Sridhar, for sharing.
Thank you so much, sir. So yeah, if anyone has some questions, they can ask me, or you can drop me an email if you need some further information. And
Thank you. And it's nice to see that from where you actually changed it to the medical field and for the betterment of the society. Anyway, it is good to know such things. Otherwise we will not know such developments. Thank you, Dr. Sridhar. And
there's some questions in the chat.
Yeah.
Okay. Okay, I have not seen that.
I cannot see them.
I have to read that.
Just a second. Let me see. Yeah. So regarding the Timepics, what the limit of temporal expert? Just a second. Wait let me. Yeah. The time resolution for the Timepics is 1.56 nanoseconds, and if you go for the T4, then it is in the picoseconds. So are the signals coming from each pixels is acquired at the same across the whole matrix? Yeah, so in the Timepics, each signal coming from each pixel is detected as individual. So I think I can't. So I think I replied to you, and yeah.
Yes.
So if you further have any questions, you can drop me an email and I can just give you the answers for them.
Yeah, that is better, I think. So with this, I think let us thank Dr. Sridhar for her excellent lecture.
Yeah, thank you so much. Thank you. Yeah.
So this session 8 concludes here. Yeah. And I thank all the two speakers, Dr. Kasim and Dr. Sridhar, for delivering excellent lectures. And I hope this will be beneficial for the budding researchers who are attending this conference. So with this, this session stops. Thank you.
Thank you.
Thank you, sir. My sincere thanks to Dr. S.N. Poti for conducting the session. My heartfelt gratitude to our speaker, Professor Qasim Abdullahi and Dr. Sheetal Kaushik Bharadwaj for their informative and stimulating talks. I also extend my thanks to the active viewers and listeners for making this a lively event. A feedback form is available on the chat box, which we request all to fill before leaving the meeting. At 3 p.m., we will start the 2 parallel sessions of oral presentations on the topics photonic materials and devices and energy materials. Please visit the program schedule to obtain the links for your respective sessions. The closing ceremony of Icmpma will be held from 4 p.m. to 4:30 p.m., during which the results for best paper presentations will be announced. At the ceremony, we will conduct a feedback session where we request all the participants to give us feedbacks on Icmpma. Thank you all and good afternoon.